Two. All right, so what we're looking at here, this corresponds to Chapter 3, Lesson 3 in the calculus book that you have. So we're going to look at positive integer powers, multiple sums and differences. So in particular, those powers, we'll look at that. We will look at a little bit about products and quotients of different functions, about negative integer powers of x, and something we call second and higher order derivatives. Okay? These rules are going to help us find derivatives in a more efficient way. What we're doing, part of that Desmos activity was exploring this a little bit. So if we look at f of x equals a times x to the n for the people that did that, or maybe people that have looked ahead at other things anyway, okay? And I think I have a proof roughly of this in a video form on that Desmos activity. So the question is, if f of x is equal to a times x to the n, some of the things that you were supposed to notice if you looked at there is that when the graph was a parabola, the derivative always seemed to be a straight line. Okay? When the graph was a cubic function, the derivative appeared to be quadratic. Okay? And so we can describe that in several different ways. And certainly if the derivative, we'll do an example here of something, let's choose a negative 5x to the 5th power. Okay? And figure out what the derivative of that is. So that's not derivative yet. Okay? If we want to know what the derivative of that, our definition of the derivative said that that would be the limit as h goes to 0 of negative 5 times x plus h to the 5th power minus negative 5x to the 5th power all over h. Now, as some of you have already figured out, and the rest of us will know before the end of the period, there is a shortcut to doing this derivative. Okay, there's a faster way of doing it, but what you need to know, also need to know, is that every year that I have taught Cornerstone Calculus, so through Central, the first question on the final has asked you to do a derivative this way with the limit definition. And if you don't do that one with the limit definition, then you get 0 points on it. Okay, so knowing how to do it this way is important, at least for that first problem, but definitely don't do it this way for anything other than problems where it specifically asks you to use the limit definition of the derivative. Okay. So this then becomes the limit as h goes to 0 of negative 5 times, and I need to know what x plus h to the 5th is. Okay, well, that's where my handy Pascal's triangle comes in. Okay. Gives me what my coefficients are going to be, so I'm going to have a 1 x to the 5th, because this was a 5th power, so I've got all x's, no h's in the first one, plus 5, 4x's, 1h, plus 10, that's 3 x's and 2 h's, and a 10 again for 2 x's and 3 h's, and a 5 for 1x and 4 h's, and a 1 for no x's and all h's, plus 5x to the 5th all over h. Will be the limit as h goes to 0 of negative 5x to the 5th minus 25x to the 4th h minus 50, oops, can't write in a straight line, x cubed h squared minus 50 x squared h cubed minus 25 x h to the 4th minus 5h to the fifth plus 5x to the fifth. And I've got a minus 5x to the fifth and a plus 5x to the fifth, and that, of course, is all over h. When you're doing it this way, everything from this part, the whole f of x that you subtracted off of there, should completely subtract off if you've done this right, so that everything that's left has an h in it. And so we will take that out, limit as h goes to 0. If we factor an h out of everything, in fact, everything has a negative 5h that I can factor out. So we'll do negative 5h, and that will leave me at 5x to the fourth plus 10x cubed h plus 10x squared h squared plus 5xh cubed plus h to the fourth. It's all over h. And h divided by h is 1 as long as h is not equal to 0. And we're taking the limit as it's going to 0, so not actually getting there. And if we notice, we've got h's left here, 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 and here. And as those as h goes to 0, all of these things go to 0. And all that remains is this. So my limit is 5x to the fourth. And so I can see that process in here, and what happened is that my fifth power that was in there ended up getting subtracted off, and the only thing that was left that didn't have an h in it at the end, when I canceled everything out, was the fourth power, 1 degree lower. And that's what happens in derivatives and polynomials. It's easy to describe in polynomials. The degree is always 1 lower than it was. Okay? And this, I missed something. Oh. Where did I miss it? I'm going to pause for a second in the recording. Okay. So I forgot about this negative 5 that is still out there as well. So that negative 5 times that 5, that gives me a negative 25 x to the fourth. Okay. To be careful to make sure that I don't lose track of things along the way. So the number out front there, if I didn't have that negative 5 that was this negative 5 here is this same negative 5 that was right there, I would have been left with an 5x to the fourth. Okay? And the 5 ends up being there because the power was 5. Okay, so this 5 is there because of that 5 that was right there. I could have made that a little bit more clear by maybe doing a derivative of negative 7x to the fifth, and you would have seen that a little bit more obviously. Right, but the moral of this story is that if you have a function that looks like a times x to the n, that its derivative is still going to have this a as a part of it, but the power that was up there is going to come down here, and then you are going to reduce the power by 1. So this rule, and normally if we were in class every single day, I would have had you playing with this and making this incredible discovery on your own. But we don't have that luxury with the time frame and structure that we have right now. So some of these things I just have to give away, and it's not as fun. The a that's out in front here, this a, okay, from a transformation standpoint, I understand that that's just vertically stretching things, right? And if derivative is about slope, and I vertically stretch something, well, that makes, when I vertically stretch it, makes it taller and steeper than what it was. And so it makes sense that my derivative is also vertically stretched, so that the derivative of this is vertically stretched by the same amount as the function was vertically stretched, because I made all those slopes of the tangent lines steeper by that amount. Okay. So when I made the curve steeper by vertically stretching it, I made the slopes of the tangent lines to the curve steeper by exactly the same amount. Okay. Let's summarize some of these rules here a little bit differently. So these are differentiation rules or shortcuts. I've got 4 of them on this side, on this slide. Okay. First one says the derivative of a constant function is 0. Okay, constant function says it doesn't matter what the input is, the output's always the same, and that creates graphically a horizontal line. And if derivative is about slope, then the slope of a horizontal line is 0, so derivative of a constant is always equal to 0. Okay, here's our power rule that we just did here in the second one. If we're doing powers of x, then we can just drop that power down and then reduce the power by 1. Okay, so the old power comes down as a multiplier in front, and the power gets reduced by 1. From a polynomial standpoint, as we're looking at this, I always think about a derivative as taking one of the wiggles out of a graph. Okay, so a degree 3 function might look like this. Its derivative just looks like this. Okay. And so this original function that had 1 high and 1 low now just has the 1 low, and it's less wiggly than what the original function was by exactly 1 wiggle. Now, that's not all the functions that we know deal with wiggling necessarily in exactly that same way. The constant multiple rule, we kind of addressed this in the last problem as well. It says that the derivative of a function that is being multiplied by a constant is just the constant times the derivative of that function. Again, because it is multiplying out in front like that is a vertical stretch, and so it makes the slope of the function change by that amount, so the slopes of the tangent lines also change by exactly the same amount. Okay, so that rule makes a lot of sense. And this one, the big time saver, the sum and difference rule. Okay, if u and v are differentiable functions of x, then the derivative of a sum is equal to the sum of the derivatives. So that says if we have a polynomial, let's say f of x is equal to 3x squared minus 5x plus 10, and we want to know what is the derivative of that. Well, we can do the individual derivatives of these things and just add the answers of those together. Okay. The derivative of 3x squared, well, we've got the constant thing out in front here. Derivative of x squared, we follow that. The 2 would come down. The 3 is there because I'm multiplying by a constant. The 2 comes down. 2 minus 1 is 1, so that's 3 times 2 times x to the first power. Minus, okay, well this part's just linear. This is a line with a slope of -5, and derivative is about slope, so this just becomes a -5. I should have done that in red because I underlined it in red. So we'll make that the -5 right there. And then, of course, this one is a constant function, so its derivative is a 0. Horizontal lines have a slope of 0. So the derivative here is 6x minus 5. Okay, it was quadratic, now it's linear, it took a wiggle out. That part all makes sense. And I don't have to think of this as a 3-term quadratic. I can deal with each term individually along the way to come up with that derivative. Really is here. By the end of chapter 3, which is a fairly long chapter, we're in section 3 of it right now, and the way we do it, there are like 10 sections. Okay? And the reason why it's long is because our goal by the end of it is to be able to take the derivative of absolutely any function. Okay? And so we have just already in what we've done here, this is every polynomial. We can check that off the list. We can now, with this set of rules, we can do the derivative of absolutely any polynomial. Okay, and we can do it quickly. We've got all of these other functions though. Okay, we have functions that we did when we did the parent functions, right? We had all kinds of different power functions that weren't exactly parts of polynomials, but we've got radical functions. We've got the trig functions. We've got exponential functions, we've got logarithmic functions. What other kind of functions did we do? I mean, everybody was assigned a parent function. Is there anybody that had one that I haven't covered here yet?
Power function.
Okay, so the power functions, the ones, if the powers are positive integers, we've taken care of that. That reminds me though, reciprocal. Okay, those reciprocal functions and rational functions. Of course, our rational functions were a ratio of polynomials, sort of related to reciprocal functions, sort of related to polynomials. So we've got all of these different things, and there are others that you may not even know about yet at this point. Okay. So there's these parent functions that we need to be able to figure out what the derivatives of them are. And then there are combinations of these. If one way to combine functions is to add or subtract them, and so if we are adding or subtracting functions, we just had a rule for that. That said, if you know the derivatives of all the individual terms that are being added or subtracted, then you just do those and you add or subtract them the way that it's set. Okay? But we also might have to multiply those together, divide one by another one, and then there is composition of functions. Okay? Where one function is evaluated at another one, and we string those things together. That's another way of combining these functions, and those build and model new and different looking things, and we need to be able to do the derivatives of those as well. Okay? And if there's trig functions, then there's probably also inverse trig functions. That we want to be able to do those. Okay, so we're going to kind of blend these things along as we go. We already took care again of the adding or subtracting. Um, the multiplying, dividing, and composition, we're going to kind of blend in as we go, and we'll be able to do those kinds of combinations before we necessarily know what the derivatives of all of these different kinds of parent functions are. Okay? And I will tell you, there are some functions coming that we kind of have never seen before. Okay, and they're fairly strange, but the promise is that if you stick with us, and by the time we get to the end of chapter 3, you will be able to take the derivative of absolutely any function. It's a nice part about calculus here. And I'll just scroll down that screen for posterity's sake, so we can see what those look like. And I'm going to start recording again. The temptation after the addition and subtraction thing is to say, well, if I had two things added together and I could take the derivative of those and just add them together, then why can't I do that for multiplying? Okay. And if we tried that and looked at this and said, well, what's the derivative of 3x plus 2? Well, it's linear, the slope is 3, it's a power rule, we could think of it that way as well. This one just has a derivative of 3. And this one has a derivative of 5. And if we multiply those together, we just get 15. But this was a quadratic, and that's not linear anymore, that's a constant function. And if we looked at the derivative of this over here, we know that what we should get as an answer is 30x plus 7, and that is very definitely not 15. So the same kind of thing that worked for addition and subtraction does not work for multiplication. If it doesn't work for multiplication, it's not going to work for division either. Because multiplying and dividing are basically the same thing. Okay. All right, so one solution to this, and the way that we're looking at it right now, is that if we see something like this where these multiply together, that we actually multiply them together and we get a nice easy polynomial, and we can do that. Okay. That's no problem at all. But the reason that the multiplication doesn't work this way, okay, if I thought of, and we'll generalize this here and call it an h of x times a g of x. Okay. When these things are multiplied together, it's kind of like this thing out here is that constant that I throw out in front that stretches the derivative of g, right? And so this is creating numbers. The difference is that the amount that it stretches by is different every time. Okay, if all I had was some constant times g of x, then I know that this would just be a times g prime of x when I did the derivative. Okay, and each of these tangent line slopes is getting stretched vertically by a. Well, over here, it's the same kind of idea. Each of the derivatives of my g of x are getting stretched vertically by a, but the amount of that stretch is different every single time. Okay, because the values of h are different all the time. It's probably not a constant function. So, yes, the derivative of g of x is involved, but the amount that it's getting stretched by is different. But we also could view this the other way and say, well, what if this is the stretching thing? This function g of x is correspondingly stretching the slopes of the tangent lines of h. And so they're working together here. One is stretching the other while it is correspondingly being stretched by the first one. And we get a combined effect of those two mutual stretchings when we do this. And so it is, in the first case, if h of x is the thing that's stretching the g of x's, then that expression would look something like that. But then on the other hand, the g of x is stretching the h of x's. And the net result is a combination of those two things at any given point. It's a real informal argument for this, but if we said that f of x was equal to h of x times g of x, then this is what the derivative of f of x will look like. Okay? This is called the product rule. And you can remember it like this, or you can remember it the way my calculus teacher in high school taught me, and I still remember it from that, so it was pretty good. We just memorized this in words as the first times the derivative of the second plus the second times the derivative of the first. Okay, and he was not particularly musical, but more musical than I am. Okay, and he kind of halfway sung this thing, which doesn't work for me. But memorizing it this way, first times derivative of the second plus the second times derivative of the first. And anytime I do a product rule in a problem, that phrasing goes exactly that way through my head, and I look at it and I write down the first function and I write down the derivative of the second, and I add and I write down the second function and I multiply by the derivative of the first, and then simplify from there. So first times derivative of the second plus the second times derivative of the first. If I did that in my problem up here, right, instead of it looking like this, which was very wrong, okay, if I did the first function, which is 3x plus 2, and I multiplied it by the derivative of the second, and then I added the second function times the derivative of the first, we'll distribute a property here. I get a 15x plus 10 plus 15x minus 3, which reduces to 30x plus 7, and those things are equal to each other. Okay. So I can verify by that one example anyway that that product rule works. All right, I am at that point out of time.